We conclude our discussion of linked lists with two final topics. The first topic is multi-level lists, including an example illustrating their use. The second topic is a summary of the approach Java has used implementing lists in the Java collection framework. A multi-level list is a list that contains sublists. The node of a multi-level list typically has three components: a data element and two references. Multi-level lists are the fundamental data structure in some programming languages such as Lisp. These lists are very similar to trees, binary trees in particular. To illustrate the use of multi-level lists, we will examine an example that performs list reversal. The program consists of several classes. The multi-level list class defines lists of this type. The multi-level list GUI class defines the user interface that will allow the user to enter multi-level lists and perform either type of list reversal. To be syntactically correct, a list must contain integers, and those integers must be inside parentheses. The parentheses should be nested to indicate sublists, and all parentheses must be properly balanced. Entries that fail these syntax requirements will throw the invalid list syntax exception. The inner class node that defines a node of a multi-level list has three components: the data contained in the node, a reference to the head of a sublist, and a reference to the next element in the list. This program allows the user to enter a multi-level list and then either reverse the list only at the top level or at all levels. The multi-level list class contains several recursive methods, all worth studying. All three are good examples of how effectively recursion can simplify operations on linked lists. One copies multi-level lists, another reverses them only at the top level, and the third reverses them at all levels. We will examine the one that reverses them only at the top. The method reverse top is passed the head of a multi-level list and returns the head of that list once it has been reversed at only the top level. This method has two base cases. The first is when the head of the entire list is null, in which case it returns null. The second reference refers to the second node in the list. The other base case is when second is null, which means the list only has one node at the top level. In that case, the head of the one node list is returned. What was the first node will now become the last node, so the rest reference is set to null. Then a recursive call is made to reverse the rest of the list. What was the first node is now attached to the end of the reversed rest of the list, and the reversed list is returned. The method that reverses the list at all levels is a bit more complicated and is a doubly recursive method. Okay, so let's run this program to see exactly how it will work in both of the cases, and I'm going to input a list here that goes several levels deep, and let me make that 1, 2, 3, 4. Go one more level deep here. 7, 8, and 9, 10. Okay, so let's create the list, then show the original. Reversing it at the top, we should only see the elements at the top, the 1, 2, and the 9, 10, being reversed, which is exactly what we see. So the part that's in the middle hasn't been changed. When we do a reverse all, the number should come out looking totally in reverse order, which is exactly what has happened. Our last topic will involve discussing the kinds of lists Java provides, and a discussion of which one to choose based on efficiency considerations. Both the ArrayList and vector classes implement lists using arrays. Both are dynamic and allocate larger arrays when the existing one is full. The ArrayList increases the size by half, whereas vector doubles it. Although method synchronization is beyond our current discussion, we will note that the methods in the vector class are synchronized, whereas those in the ArrayList class are not. Vector is a legacy class that was in the first version of Java. ArrayList was introduced when the full Java collection framework was added. Because the methods in ArrayList are not synchronized, they run faster and so are the better choice if synchronization is not required. The linked list class is implemented with a doubly linked list and implements the queue and deck interfaces. All three implement the list interface. The stack class is implemented as a subclass of vector. As we've already noted, because Java does not support representation inheritance, this was a poor design choice. Because either an array list or a linked list will work when a list is needed, it is important to understand some efficiency trade-offs between them. To make the decision whether to use an array list or linked list, the operations performed most often should be considered. The ArrayList class efficiently implements the ability to extract elements at a specific index, because an array is the underlying implementation. The linked list class efficiently implements insertions and removals at both ends, because no shifting is needed. Neither is more efficient at insertions or removals in the middle. In the array list case, shifting is needed, and in the linked list case, a linear search is needed to find the position. The other resource whose efficiency is important is memory. There are also trade-offs to be considered here. The ArrayList class usually has more allocated memory than is used. That will be especially true when the ArrayList is empty initially, or after it is expanded because it became full. The linked list class requires twice as much memory for each data item because each node also contains a link. Doubly linked lists might require 3 times as much if the links are not compressed. Assuming the linked list is implemented by compressing the 2 links, an ArrayList object will use less memory than a linked list object whenever the ArrayList is more than half full. We conclude by summarizing the efficiency issues. The get and set operations are much more efficient in an ArrayList because they execute in constant time compared to linear time for a linked list. Adding to the front of an array list is more costly because of the need to shift elements, making it linear compared to a linked list which is constant. The same is true for removing from the front. So an array list is clearly the better choice when numerous gets or sets are needed, and a linked list is the better choice when adding and removing at both ends is needed.